Okay, so this is a presentation about multi-thread algorithms. So these are the table of contents. This is what I'm going to discuss in the coming few hours in this class. So the motivation to understand and to analyze the complexity of algorithms when run on a multiprocess systems. So what exactly are we studying, or what exactly we have been doing in algorithms class is basically we'll look at an algorithm and then we try to compute the complexity of the algorithm as if it is getting executed on a single thread. Means each of the steps they're executed sequentially, one after the other, one after the other. This is also called the serial execution model. So when it comes to the real world, it might not be an ideal model. It might not be feasible to adapt the same theoretical complexity to understand the practical implications of the algorithm on today's computers. Even a mobile phone is operating on an 8-core processor system these days. So the discussion, the study of multi-thread algorithms and the learning to estimate the complexity of multi-thread algorithms can give a good understanding or perspective in analyzing the complexity that applies in today's worlds, today's multiprocess systems. So here is an example of computing a Fibonacci number. Fibonacci number, like this is a basic. This is a very small code that computes Fibonacci number for n. So let us try to execute this step by step, sequentially. So we'll start with n, that is f of n. Let us assume that n is 4. So the execution starts with a function with the value n as 4. As n is not less than or equal to 1, we go ahead and we want to calculate x is equal to f of 3. So which means f of 4, it just calls f of 3, and f of 3, it again starts executing. It calls f of 2, which calls 1. Now 1 returns a value 1. Now f of 2 will call 0, which returns a value 1. Now 2 returns a value 2. 3 calls 2. 2 calls 1. 1 returns a value. 2 calls 0. 0 returns a value. Now 3 returns a value, which is I think it is 4. No, yeah, I think it is 3. And now 4 calls 2. No, 2. And then 2 calls 1. 1 returns 1. And then it calls 0. 0 returns 1. And all of this in the last statements. So what is actually happening here is that the function to calculate Fibonacci of 4 is calling 3, but until that function to calculate Fibonacci of 3 is returned, this function is waiting to call Fibonacci of 2. So basically it takes an entire this entire time it has been waiting. It is not basically, if it is sequential then it is fine, but if there are if we have a lot of resources and we are basically doing addition or something, that's it. So basically we are waiting for nothing. This process is doing nothing. So the main motive of multi-thread algorithms is to minimize the waiting, is to maximize the maximize the utilization of resources. Now, let us look at a few fundamentals of multi-thread algorithms. Multiprocessors these days, yes, as I told earlier, multiprocessors are today's trend. So they offer multiple processes to run at the same time, which is called concurrent or parallel mode of execution. Which means, as seen in the example, Fibonacci of 4, when we are calculating for the function 4, need not wait until function 3 returns. We can basically spawn a thread. We can actually concurrently execute these two parallelly. We can calculate function 3 and function 2 parallelly. So we have a few examples, and yes, one more thing. We also have to understand if we can execute a particular thing in the we also should understand if we can adapt multi-threading to a particular algorithm or not. For this, the thumb rule or the benchmark is basically every step of execution should be independent of the previous step. At least we should be able to divide the entire problem into a few sub-problems whose solutions finally form the big solution, finally form the entire solution. But these sub-problems should be independent of each other, independent of each other's results. So let's look at a few examples to understand the parallelism. Yeah. So the thing is, as long as you can, convert any problem into dynamic dynamic learning, dynamic programming, or divide and conquer. Yes, divide and conquer. If as long as we can divide a particular problem into a number of sub-problems and get the result out of the divisions of solving these sub-problems, we can basically do it on a multi-threading. We can adapt multi-threading to those solutions. So here is a small example to find the maximum in an array. So if we go for a divide and conquer rule, then yeah, it is possible we might be able to find the maximum array and adapt this multi-threading to this problem. So the assumption is we basically divide the array into two or n, the number of processes and number of sub-arrays, and we calculate a local maximum in each of those sub-arrays. Once the result of these sub-arrays is submitted, we once again get the maximum out of from the submitted solutions or the solutions of these sub-problems. So basically multi-threading is nothing but a divide and conquer, and the problems that are divided are run parallelly. So the next number is to find the number of even numbers in an array. Of course, we can, if there are n numbers, if the array is n long and we have n number of processors, the entire operation can be executed in big O of one time, like in a jiffy. You just push all of these inputs and you get true, false, true, false, true, false. And once these values, once the solutions are submitted, or once we, then we just add the thing. Once again, now you might say, how is adding multi-thread problem? Once again, we can look at it as if it is an array and divide the array into subarrays. These subarrays, in turn, we calculate addition, like sum of this subarray, and then we'll take the sum of that array. So basically, the entire thing is benchmark, divide the problem into smaller problems, independent problems, solve them, get these solutions together, and form the final solution. So, as I told theoretically, let us apply this to in a general sense. Yeah. So, to create a small problem, or to start a smaller problem, we say spawning a process. Means it creates two processes. Basically, it creates a process from the main process, which executes itself independently. We can think of it as if it is a thread. So basically, there is a main thread, and we spawn a subthread. And sync is the point where we wait for all the subthreads or all the sub processes to finish execution, so that we can come to a conclusion, or so that we can get the final answer. Now, applying these concepts to our Fibonacci calculation, we can always spawn a thread to compute to get one of the Fibonacci numbers. So in the example here, we are spawning a thread with n minus 1. So let us try to work this out. N is equal to 4. So the execution continues, and when we reach this n minus 1, f of n minus 1, we basically spawn a new thread whose value is n is equal to 3. We will not just spawn, we will continue the execution, but the execution gets interrupted when another function n is equal to gets called for n is equal to 2. And after we call this function, we wait at a particular point. We wait there for both of these functions to sync. Now what happens at n is equal to 3? It spawns a thread for n equal to 2. And what n equal to 2 does? It spawns another thread for n equal to 1, but n is equal to 1 returns immediately. As well as it calls another function which is n equal to 0, which also returns. So here is the sync. So this is where both of these processes sync. And n is equal to, as it called n equal to it one more time, it calls n equal to 1, which is n equal to 1, which returns immediately. And let us have a sync point here. So once this sync is done, it comes here. Once this sync is done, it comes here. So same thing continues with n equal to 2. Here 2 spawns a thread for 1, and it calls a function for 0, and it waits for a sync to complete. So these values come here, and once the value for n equal to 3 is complete, it goes for sync. So the values returned are 1 and 0. So the value returned is 1. So we have 1 here and we have 1 here. So 3 returns 2, and we have a 2 here. 1 returns a 1, 0 returns a 0. So 1 plus 0 is 1, and 2 plus 1 is finally the answer, which is 3. Is it true? Yes. This is how we can visualize the entire thing, the entire process of calculating n equal to 4. We can clearly see that we have saved a lot of steps, a lot. So yes, now coming to looking at how the process went on, how the calculation went on. We can say that this is a cyclic graph, a directed acyclic graph. So basically each spawning there are no cycles, and each process or each new process is denoted with the vertex. So we can say that these are instructions that spawn new threads or that call new functions. And then there are edges which connect these calling processes with the call processes, and these edges, they denote dependencies. So if there is an edge between two vertices, U and V, means process V should be executed before process U. So as we can see here, that there is a thread from here from 2 to 3. So there is a dependency. Unless the execution of this particular site is not complete, or this particular instruction is not complete, we cannot go ahead with the execution of this instruction. Same thing here. Unless the execution of this is not complete, we cannot go ahead. Same thing. So these edges, they denote dependencies. So this is called DAG, or directed acyclic graph. And now counting on the complexity front, there are usually two metrics. There are two metrics used. So one of them is the total time to execute the entire operation on one processor. So one of the metrics, it basically gives the measure of the entire work done by all of the processors. Let us say there are like infinite number of processors, and we spawn all of the threads that we want. So the work metric is it defines the work done by all the processors that were active, or all the sites that were active. So basically here we can see that the number of processes is the number of nodes that were created, because that is where the execution was taking place. So we can count as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So the work done is 17. And now span is the longest time any particular process should wait. So basically the work done, or the time taken for the entire algorithm and the system to take the input and produce an output is divided into these two. Is basically how much time it took to work, is how much time it took to execute the thing, and how much time one of these particular sites had to wait to continue its execution. So that is the entire time taken. So for the output at 3 to arrive, each of these sites should do their task. Each of these sites should execute their task and produce an output. But 3 cannot produce an output until it gets its output from these two. which are in a way dependent on all of the others. So basically, the entire time is, the time of execution plus the time of waiting. Now let us assume that all of these processes, if they work at exactly the same rate, then we can say that then we can see that the maximum wait one should do is the length of the longest path, so which is 1, 2, 3, 4, 5, 6, 7 and 8. Yeah, which is 8. No, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, this is how it follows. So this is the longest length. So as we can see here, so this is the entire time taken, or this we can call it as the complexity of the entire thing. So the actual running time of multi-thread computation depends not just on its worker span, but also on how many processors are available and how the scheduler allocates the strands to processors, etc. So running time on a processor is indicated by subscript P. So the running time of entire algorithm on a single processor is basically your serial execution, and these spawn and sync keywords, when they are removed, the entire thing is basically the entire algorithm is basically the serial form of the serial form. We are not doing any new thing here. We are just spawning the threads. So T infinite is a running time on unlimited or infinite number of processors. So an ideal processor on P can do at most P units of work. So total work to do is T1. Thus, speed up of a processor is defined as T1 by Tp. Parallelism of multithreading is given by T1 by T infinite. Scheduling the performance depends not just on the